In this video we're going to look at the modulus of a complex number. And to start, I'd like you to recall what we meant, or what we mean by the modulus of a real number. Here's the real line. Let's look at the number 3. The modulus of 3 is 3. In fact, if x is a positive number or 0, the modulus of x is just exactly the same as x. However, that's not the case for negative real numbers. For instance, negative 2, that you know the modulus of that is positive 2. We could define for negative values, real values of x, the modulus of x to be negative x. In other words, the negative of negative 2, which gets the positive. One way I'd like you to think of this is that we're looking at the distance of each real number from the origin, so that the modulus would be a measure of the distance of the real number from the origin. So this measures the distance from the origin. So bearing that in mind, let's now look at the complex grid and use that same idea. For instance, let's look at the complex number z, 3 plus 2i, and ask ourselves, what is the distance of that point from the origin? What is the length of that line? Well, I think you would use Pythagoras. We know that's 3, and we know that's 2. There's your right-angled triangle. Therefore, the length would be the square root of 3 squared plus 2 squared. Another example, for instance, if we take the complex number minus 1 plus 4i and ask ourselves, what is the distance from this point, again, to the origin? Then we have another right-angled triangle where we have two lengths. This length is 4, this length is positive 1. So the length of this line would be the square root of, I should be saying 1 squared, but up here the real part of this complex number is negative 1. For a reason you'll see in a minute, I'm going to square the negative 1. Negative 1 squared is exactly the same as 1 squared. Because you're squaring, the negative disappears. Negative times negative is positive. And this length here, which is 4. So the length or the distance of this complex number from the origin is given by that. So if we extend the idea of the modulus that we knew in the real number case to interpret it as being the distance of a complex number from the origin, then in the case of, for instance, 3 plus 2i, the calculation we would do is the positive square root of 3 squared plus 2 squared, which would be 9 plus 4, that's square root of 13. And in the case of the complex number w, which is negative 1 plus 4i, it would be the square root of, and we're going to use the negative 1 and square it, plus 4 squared, and that would be the square root of 17. So this leads us to a definition. In general, if z is the complex number x plus I, y, then the modulus sometimes it's called the absolute value, and it's written as z bar, is the distance of z from the origin O of the complex plane. In other words, z modulus is positive square root of x squared plus y squared. Now, saying x squared, we notice up here that if x is negative, then this still is valid using Pythagoras, because -1 squared is the same as 1 squared, which is the distance from the origin out to the point -1 there. Now, it's nice to know that that coincides with the notion of modulus of a real number. For -4 as a complex number, let's look at that. -4 we know is -4 plus 0i. So the modulus of -4, the modulus of this complex number by this definition would be the square root of the real part squared. That's the -4 plus the imaginary part squared, 0, which gives us the positive square root of 16, which is 4. Incidentally, when you write square root of 4, the real number 4, we mean positive 2. That does not include the negative value. Sometimes you might see this written, x squared equals 4. If we're dealing with real numbers, x squared equals 4, therefore x equals the square root of 4. And therefore x equals 2 or -2. Now that's wrong, because when we write square root of 4, that means positive. So we would have to write root 4 or negative root 4. So if we do want -2 as the square root of 4, then it's negative, and we therefore have to put a negative in front of the square root sign. After all, when you do the quadratic formula, -b plus or minus the square root of b squared minus 4ac, if the negative was implied by the square root sign, you wouldn't need a plus or minus outside. You just need a plus. So writing square root of 4 positive. If we want the negative, we put a negative in front of it. So there we have examples of the modulus of a complex number. Now, it would be nice at this stage if you had a shot at some examples. So let's just put the heading there, and I'll ask you to try and evaluate the following. Modulus of 1 minus I, the modulus of -3 minus 2i, the modulus of I, and the modulus of the complex number whose real part's negative, 1 over root 2, and imaginary part is positive 1 over root 2. So stop the video and see if you can try these questions. Okay, how did you get on with that? Let's have a look at question 1. Modulus of the complex number 1 minus I will be the positive square root of 1 squared plus, and the imaginary part of this complex number is -1. So we square both of these. 1 squared, 1, -1 squared is 1, 1 plus 1 is 2, so we get the positive square root of 2. On the diagram here, 1 minus I, this distance from the origin is root 2. Second one, complex number -3 minus 2i, modulus of that, square root of -3 squared plus -2 squared. That is square root of 9 plus 4, which is the square root of 13. -3 minus 2i, that's a complex number down there. That distance is square root of 13. Third example, the modulus of I, square root of real part is 0, imaginary part is 1. We get the square root of 1, which is 1. I lies at a distance of 1 from the origin in the complex plane. And the fourth one, this rather complicated looking complex number, modulus of that, square root of, real part is negative 1 over root 2, we square that. Imaginary part is 1 over root 2, we square that. Negative 1 over root 2 times negative 1 over root 2 will give you positive 1 times 1 over root 2 times root 2. And by definition, root 2 times root 2 is 2. 1 times 1 is 1. So we get 1/2 for that. Similarly, 1 over root 2 times 1 over root 2 again is 1/2. So we get the square root of 1, which is 1. So the complex number negative 1 over root 2 plus 1 over root 2 lies about there, is at a distance of 1 from the origin. Now, interesting to note in this diagram, you imagine this circle, unit circle about the origin. We have on that I, negative 1, negative I, and 1. Also this complex number we've been looking at, which sits about there. All of these complex numbers have modulus 1. They're at a distance of 1 from the origin. So if we were to look at complex numbers whose modulus is equal to 1, any complex number that satisfies this equation would lie on this circle. Now we'll see in some later videos that I'm going to do this idea in more detail. Okay, one last example, we'll get into some proofs. And again, this is one that you should be trying before I do this. So prove, I'll call this example 5, that the modulus of negative z is equal to the modulus of z. And example 6, prove that the modulus of the conjugate of z is equal to the modulus of z. Now, could you stop the video and do actively try and solve these questions? Right, let's have a look at these. So number 5, proof. And this is very general. We have to take any complex number. So you'll be familiar now with the method we use. We say let z be x plus iy. Then negative z we know is negative x minus iy. The modulus of z is the square root of x squared plus y squared. And that will be the same as the modulus of this, because negative x squared plus negative y squared, that's the real part's negative x, the imaginary part is negative y, we're squaring both of these, it's identical to x squared plus y squared. So that's the proof, relying on the fact that negative x squared is the same as x squared and negative y squared is the same as y squared. And number 6, again, we'll let z equal x plus iy. Then we know that z bar is equal to x minus iy. And again, well, let's take z bar first. Square root of real part is x, imaginary part is negative y, and that of course is the same as x squared plus y squared, which is the modulus of z. So that's our proof. Interesting to look at these on the complex plane, that if we have, for instance, z sitting here, x plus I, y, then the negative of z is, remember we took this line and rotated it by pi radians, giving it a half turn to produce negative z, same distance out the other side through the origin, but rotating, if you like, the position vector of this point 180 degrees, pi radians about the origin. There's negative z, and the distance is the same. And remember the conjugate surd, z bar, which is x minus iy, we got from z by reflecting in the real axis. So these points are all the same distance from the origin. They all lie in a circle which has radius modulus of z. Modulus of z is this distance here.